So an honour again to be here again at DARC25 to be able to illustrate some of the research and advanced prototyping work that is happening within Elbit Systems UK. The first element of this prototyping work that I want to show you today is some work that we've been doing on geolocational positional discrimination of parametric, ambiguous or category indistinguishable differences in lines of bearing correlation. What that means is where we have a passive emitter that has a line of bearing and there is more than one emitter of the same type, we get a number of crossing points, of which some of them are going to be true and some of them are going to be false. And the work here is to be able to distinguish between the true ones and the false ones. And this work is quite important when there is a number of ambiguous elements, because as the altitude gets higher, what we will find is that the number of crossing points increases, and also if we add more sensors in there, we get more opportunities for crossing points. So what we basically find is that the number of false positions grows exponentially relative to the true positions. And if we also have mission data sets which are not mature, then we can expect quite a lot of unknowns, which is effectively the same classification, an ambiguous or indistinguishable category. And what we can imagine, therefore, is that this problem grows quite a bit when we're doing coalition warfare, if our mission data sets are not built to the same standards, or in fact at the same maturity, or in fact using the same data. And so the solution that's around this is not to use parametric comparison, and in actual fact what it's using is a trigonometric and probabilistic model that is behind it, and therefore it is actually fairly generic and is relocatable to other domains. And what it can do is it removes the false positions at the detection stage. And that means we don't have to use progressive tracking. We're using this right from the start, so we get rid of the data load right from the beginning of all those false positions. It improves our situation awareness regardless of our NDS quality or mixes of those qualities. And therefore it is allocatable to multiple platforms in the naval domain, land domain, also clearing up air pictures for uncorrelated lines of bearing, and perhaps even underwater tracking and acoustics. What we can see here is two diagrams here. The green lines are the line of bearings, and in the one below it also does fusion with range known stuff as well. This model, that's actually just radar detections, and they've been fused down to the number. What you can actually see, and this is actually the channel area, and I'll just move to the next slide. What we can see is that the green lines are actually the line of bearing correlations for line of bearing lines for passive sensors. What we can see is that there's these little green circles kicking around where they cross. Those are the positions that have been declared as false ranges. And the red lines that are moving, it's actually running now, you can see have been declared as the actual position. Now it also does correlation with range known, etc. data, and you can see some of that in this demonstration that's going here. But what you can see is we are seeing an amount of positions that are able to be resolved, and some of them have been removed. And the red that is there is actually showing us the inner and outer shipping lane on the channel. So that looks kind of like the right thing. You can also see two sneaky boats making their way in as if they were like immigrant boats. So that's quite good. So that's actually working. That's still work in progress. There's still complexities to be taken out of that. But the model is using physics engines, etc. with that. It's using beam shaping, all those sort of things, and propagation models to go with it, and a notion of the horizon, etc. The next part of the work that I want to therefore show to you is something called LCA and OpenCPI. And OpenCPI apps to become runtime modifiable and redeployable. And essentially, part of the LCA, which is now called sticks, is a number of abstraction layers which build up to be able to try and make applications developed to be reusable, redeployable, reallocatable. And so it builds up from a sort of OpenVPX backplane to GVA data structures. It elaborates that with extra stuff for modular Open Radio, which enhances the GVA. And then we have this Open CPI, which is kind of like a board support package that allows us to abstract the hardware specifics that are occurring on such boards for either FPGA or processor boards, etc. And so what that's actually doing is it's providing an abstraction to that hardware, but when it's compiling to FPGA, that's often quite a long compilation process, and the result of what comes out of the compilation process tends to be a fixed resource. So what we're actually doing is adding an abstraction there to put a control to do dynamic dynamic resources to be allocated and deallocated. So if you like, what we have done is we have provided a model where we channelize the OpenCPI module, and what we're then doing is using the hypertext markup language to be able to control the resources in those channels such that we're able to provide dynamic allocations and reallocations of techniques. And so what we had proposed was a hypertext markup language that works in construction right now. And it's to provide an exchange format, and it's specification interface based. And what that means is it's describing how something executes, not the implementation. The implementation will occur on the tactical unit when it conforms to that specification. So it's a bit like HTML in a browser or PostScript in a printer, if you like. And that gives it a resilience to the hardware specifics, which is very in tune with the stick side. But what this allows us to do is allow multiple apps and re-downloadable. Okay, a bit more akin to a mobile app. And then we, of course, build on all those VPX and reuse and hardware values that it gives us, and also taking into account the sort of GVA and MORAG extensions as well. So just to illustrate what that is, because I don't actually have a demonstrator to show you today, what you basically imagine is that we have a hypertext language which describes an emission, and what we can do is we can pass that to a technical unit who will play that, and we'll have confidence because it's a specification that will play correctly, and then we can maybe give it another one as well, so there's multiple apps there, and then maybe we can put one on another tactical unit, and then maybe we can move from one unit to another unit. And that's kind of the diversity and the dynamicness that we want to be able to do with this language, to be able to dynamically allocate resources on the fly in real time, such that we can make these tactical units respond to a control signal very, very fast. And so they can be used for unattended sensing, etc., while also giving a resilience to the hardware specifics that might actually occur in those hardware, such that we have a way of doing that. This is all part of our Centre of Excellence initiatives within Elbit Systems UK. Any questions?